Hello, in this lesson we're going to address creating and addressing numeric arrays, which really are the heart and soul of MATLAB. The learning objectives are to create one-dimensional and two-dimensional numeric arrays using several different methods. And the second one is to address individual elements and ranges of elements from a numeric array using MATLAB subscript notation. So the array really is the fundamental form of data structure that MATLAB uses to store and manipulate data. And so to put it simply, an array is a storage container for different types of data. MATLAB supports many different types of arrays based on the data that it contains. There's some homogeneous data types, numeric arrays, which we're dealing with today, character arrays, string arrays, logical arrays, and then there's some really useful mixed data type arrays, such as cell arrays, table arrays, which we'll deal with later in this course, and structure arrays. Quick note about an array versus a matrix. So recall that I said that an array is a structured storage container that we put things into, and they don't necessarily have a mathematical purpose. But in our everyday usage, a matrix is a more specific form of an array. It's still a storage container, but it's defined by its rows and its columns. Matrices are extremely useful in practical mathematical calculations, and we will also explore matrix algebra later on in this course. Now, for our purposes, we're going to use these terms interchangeably. The simplest numeric array is a one-dimensional array. And a one-dimensional array is just a list of numbers, which is placed in either a row or a column. And I should point out, as another note on terminology, these one-dimensional arrays and matrices are often called row vectors or column vectors. And that's kind of unfortunate because a vector is mathematically defined as an object that has both magnitude and direction. Here we're just dealing with numbers. I'll try to keep my language pure, but I'm pretty sure I'm going to slip up too. So let's take a look at this table that has historical population data for Denver. And so we're seeing the years from 2017 to 2021. And really it's a list that are in these columns. And each list can be entered as elements in a matrix with the numbers placed in either a row or column. And what we'll do is we'll recreate this list using our array data structures. So let's first off by dealing with the years, and we want to make this a row matrix. We do that by assigning years row using a left square bracket. We'll type in 2017, 2018, 2019, 2020, and 21. And when we put this in, you can see that we have a row matrix that has those dates included. And to create this row matrix, we put a space in between each of the values that we inserted, or you can also put a comma. To create a column matrix out of the same data, so we'll call this years column, instead of a space or a comma, we'll put a semicolon. So the key feature here is that a space and a comma is going to shift column by column, and a semicolon will shift row by row. Now a second way that we can enter this same data, and so let's do our years row, is by knowing that this matrix has equally spaced data, and we know the interval that is that space, we can create this using the colon operator. So years row, we can just say is 2017 colon 2021, and we'll get that same row matrix. But let's say that you don't want every year, but we want every other year. So we can say our years row by 2. We can then add another element into this command where we're saying go from 2017 to 2021, and we're going to only take every other year. So there's one more way that we can create a column or a row matrix, and that's by using the linspace command. So let's take a look at this, doc linspace, and we see that the row matrix here is going to be linspace x1 to x2, where x1 is the first value, x2 is the second value, and then it tells us it's going to put 100 evenly spaced points between x1 and x2. The other way is to do linspace x1, x2, and then give it an argument n, which n is telling us the number of elements that is in linspace. So let's try that second version, in which we say years row, and our first element, so linspace, our first element is 2017, our second is 2021, and then there are 5 that we want within that matrix. And so we get the same answer. In the linspace command, this was a pretty simple example, but linspace really becomes the most helpful when creating long, equally spaced matrices for larger data purposes or for visualization. So for example, if we want to plot y is equal to sine x across the domain from, let's say, 1.3 to 1.9, let's do x is equal to linspace, and we'll go from 1.3 to 1.9, and let's put 40 elements in there. And so I'm not going to suppress the output, so you can see that it goes from 1.3 to 1.9, and it's applying the correct interval here. It's an interval that I didn't want to calculate. And then we can set y is equal to sine x. I am going to suppress that output, and then we can plot this really quickly. I'll just plot x and y, and you can see that we now have a nice smooth curve showing our y versus our x. Let's switch now to creating a two-dimensional array or a matrix. And this is simply a collection of numbers that are arranged in rows and columns, much like a table. So this is how we normally think of what a matrix is. And let's take a look at our cheat sheet that we have here, in which we can, in creating a two-dimensional array from a known list of numbers, we'll borrow this format, and you can see that the matrix name is going to be equal to, we have our open square brackets, and then we end it with our closed square brackets, and then we're separating each of the rows by semicolons. Let's use this format to input the first 3 rows and 2 columns of our Denver historical population data. So we'll change our matrix name to Denver population table, and our first row, the first element of the first row, is 2021, and then the next element is, we're just going to say 2.86 million. So we can put a comma, 2.86, and then for our second row, it's 2020, and then comma, 2.83, and then for the last row that we're going to include, it's 2019, comma, 2.79 million. And so you can see that Denver population table is now a 3-row by 2-column matrix that is mirroring the images that we have here using that syntax from the cheat sheet. There's a good chance that your table doesn't look like this, that you're following along, and it's because I changed my format earlier. The default is going to be a format short, so if I run that command again, or if I display my Denver population table with the format short, then I bet your table probably looks like this. You can change your format. So format, and we'll call it short G, is one that gives us 5 significant digits. And that's just a nice way to look at these data, because you can see that the 2021 is preserved how we want to see it, and then also the 2.86 is preserved how we want to see it instead of using this scientific notation. Now, the way that we entered these data were a little bit weird, because what we did is we entered each row, 2021 and 2.86, and then separated each row by a semicolon. So first row, and then our second row, 2020, and then the 2.83. And the reason why that's a little bit strange is because as we look at our table here, it makes a little bit more sense to group our years together and then our population numbers together. So let's look at an alternative way to enter this matrix. And that's, instead of separating the rows by semicolons, let's separate the columns by commas. So to separate our columns by commas, we first need to create the columns. So let's go years column and create a column matrix. And we're going to use our colon notation to go from 2021 to 2019. Now in this colon notation, going from 2021 to 2019, our increment needs to be a negative increment. So let's put in our interval or our increment of -1. But now we've run into another problem. We have not a column matrix, but it's a row matrix. So this is where the transpose command comes in. And so the transpose of a matrix, which is going to switch the rows for the columns, is going to be the single quote after a matrix. And so now our years column is formatted of 2021 to 2019 in a column matrix. Now let's create a population column. And we'll do this the traditional way that we did before, where we'll enter 2.86, and then go to the next row with a semicolon, 2.83, semicolon, 2.79. So we have our population column. And then we can recreate our Denver population table by then joining the years column with the population column and separating them by either a comma, or this can also be a space. And so we should get the same result that we had before for our Denver population table matrix, with our years in our first column and then the population in millions in the second column. A critical thing to note when joining these two matrices together is that they, in this case, because it's a column matrix and a column matrix, they must have the same rows or you'll get an error. And let's simulate that error by adding another element. We'll say we got a little overzealous and we went 2.75 as the fourth row of our population column. And then if I attempt to make the Denver population column again, it's going to say I've got an error using HORSCAT. The dimensions of arrays being concatenated are not consistent. And so we needed three rows in each array, but we have 3 rows in our years array and then 4 rows in our population array, and they're just not going to fit together.